All right, welcome back to Abstract Algebra. In this video lecture, we're going to wrap up our work in section 4.3 on homomorphisms, ring homomorphisms, and ideals. And I want to tell you about something called the principal ideal. So you're looking at the goals of the lecture there. I'll just kind of outline them. I want to define what I mean by a principal ideal and a principal ideal ring. I want to give a few examples to illustrate those definitions. And then I want to end by just kind of playing around with a factor ring that involves matrices. So we can do a little bit of work in the matrix ring. It's not one of our common examples, but I want to bring it into the conversation. All right, so let's get started here with the main definition. This definition, I want to say, can be made more generally than what I'm doing it here, but for the purposes of this course, I'm only going to be working in commutative rings with unity, so I'm making that definition in a commutative ring with unity. So I'll start with a commutative ring with unity, and I pick some element of it, and then I'm defining what I'm calling the principal ideal generated by that element. And here it is as a set. I'm using the same kind of notation I use for cyclic subgroup generation, and it's not an accident. But here I take my A and I don't add A to itself over and over again in the additive group R, but instead I multiply A by all possible ring elements. Okay, so parentheses A in this setting is the set of all R times A where R runs over the whole ring. And I'm calling that the principal ideal generated by A. So I definitely owe you a justification of this term, the principal ideal generated by A. So I've got a little space to prove a proposition here for you. I'm going to try to leave the definition where you can at least see the set that the principal ideal generated by A is an ideal. All right, I'm not going to recapitulate everything in the hypothesis here, but I mean in particular that I have a commutative ring with unity. A is an element of it. Principal ideal generated by A is an ideal. Okay, otherwise we shouldn't be calling it the principal ideal. So let's prove this, or at least sketch a proof of it. So I need to show you that that thing is a subgroup, right? Because an ideal is a subgroup that's closed under multiplication by outside ring elements. So a subgroup should be non-empty. And so I'm going to start this proof by saying, well, the element 0 in the ring we proved is certainly 0 times A. So that looks like an element of this parentheses A by definition. So that's enough to show that parentheses A is not the empty set. Okay, for closure under addition, I'm going to take two elements of it. Let's suppose we've got, say, X and Y, and they're in parentheses A. And what does that mean? Well, by the definition of it, there have to exist a couple of ring elements. I'm going to call them R and S, such that, well, X is, say, R times A, and Y is S times A. So if we add X and Y together, that's adding R times A and S times A. And by the distributive law in the ring, we can rewrite that as, excuse me, R plus S times A, which is certainly an element of parentheses A, because R plus S is an element of our ring. Okay, so there's closure. I've already listed this element X, so I'm just going to use it again. The additive inverse of X, well, that's the additive inverse of R times A, and we proved that that would be the additive inverse of R times A, which again shows that that's an element of parentheses A, because parentheses A is defined to be the set of all ring elements times A, and minus R, the additive inverse of R, is a ring element. So that shows that parentheses A under addition is a subgroup of the additive group R. So we just have to show the sticky property. Okay, so I've already gotten an element up here called Y. Let's let Y be an element of parentheses A. And then let's let R be any element of this ring. And one of the things I have to convince you is that R times Y is again in parentheses A. Well, R times Y is R. I'm going to recycle our notation from up above, S times A. And that's RSA by the associative law in the ring. And that, again, is clearly an element of parentheses A. Okay, and then the last part of the proof would be to show you that Y times R is also in there, but Y times R is R times Y because our ring is commutative. our ring is commutative. So we've shown that parentheses A is a subgroup that has the sticky property on both sides. We've shown that it's an ideal. Cool. So now we can stop calling it parentheses A. We can call it the principal ideal generated by A, and we've justified that terminology. Let's look at a couple of examples. First example I want to look at is where the ring is the ring of integers. And in that ring, this notation, parentheses n, for a moment here, it's kind of ambiguous, because if you say, well, if I'm looking at that as the subgroup generated by n in the integers, I mean add n to itself any number of times and gather up all the results. If I'm looking at this as the ideal generated by n in the integers, I mean multiply n by all possible integers. Well, since adding an integer to itself k times and multiplying by k are the same thing, in that case, the notation actually means the same thing. It's one of the reasons why we're justified in using this notation. So those subgroups that we're used to, the multiples of n, they're all ideals in the integers, and they're all principal ideals. And like we said in class, every subgroup of the integers is cyclic. Every subgroup of Z is cyclic. So these things are the only ideals in Z. Sorry, I'm squeezing that in the bottom down there on you, but I don't want to reveal the next thing until I say this, that every ideal in the ring of integers is a principal ideal. All right, so we're going to christen such rings with a name. If you have a ring like the integers in which every ideal is principal, we're going to call that a principal ideal ring. You can pause this to write all that down if you want to, but yeah. And again, I'm specializing to commutative rings with unity. That doesn't have to be the case. If you take other algebra courses or you read some other books, you can speak about principal ideal rings outside of the commutative ring realm. But for us, we're just kind of sticking to commutative rings with unity. So I'm making these definitions there. But so commutative ring with unity. This principal ideal that we defined above, if the ring isn't commutative, it's actually not going to end up being an ideal. But we're going to just sort of downplay that. So we're making these definitions inside of commutative rings. So in a commutative ring with unity and every ideal is principal, I'm going to call that a principal ideal ring. Okay, you guys remember what an integral domain is? An integral domain is a commutative ring with unity that has no zero divisors. So if you have an integral domain in which every ideal is principal, then we call those things principal ideal domains, PIDs. And they form an important class of rings. The integers, I think, is a good example to keep in mind. The integer certainly has no zero divisors. Every ideal is principal. The integers are a principal ideal domain. As we make our way into the kind of end of chapter 4 and start looking at what we'll call polynomial rings, they form another important example of these principal ideal domains. Okay, a lot of terminology coming at you. Hopefully you're making a glossary or a list of flashcards, digesting all this stuff. So here I've written it. The integers is a principal ideal domain. There's no zero divisors. Every ideal is principal. As a second example, every field is a principal ideal domain. Yeah. What did we prove in class or in the previous video lecture? If F is a field, then F has two ideals. Do you remember what they are? One of them is the ideal containing only zero. That's certainly principal. It's generated by zero. And the other one is F itself, which is also a principal ideal. F is the ideal generated by, say, 1, for example. If you take all the field elements and multiply them by 1, you'll get every field element. So since the field only has two ideals and they're both principal, you're going to prove in your homework that every field is an integral domain. So there you go. Every ideal in this integral domain is principal. It's a principal ideal domain. If you want an example of a ring that's a principal ideal ring, but not a principal ideal domain, you can look at some of your ZNs. Not all of them, but I picked Z6. Z6 is not a principal, it's not an integral domain. Do you know why? Can you complete this sentence? Z6 is an integral domain because it has zero divisors. For example, 2 times 3 is 0 in Z6. But 2 isn't 0, 3 isn't 0. So if you have zero divisors, you're not a domain. But I claim that every ideal in Z6 is principal. I'm going to leave that as an exercise to you, but it kind of follows from the fact that Z6 is a cyclic group. So every subgroup of a cyclic group is cyclic, and then sort of like up in the integers, although there's a little detail to think about, adding an element to itself over and over in Z6 is kind of like multiplying by Z6 elements, as long as you're doing the multiplication mod 6. So I'm going to leave that as an exercise for you to show that every ideal of Z6, or if you want to take the sort of challenge, every ideal of Zn is principal. But Zn is not always a PID. You actually know the answer to when Zn has zero divisors and when it doesn't have zero divisors. So there's a little something I can ask you to make sure that you know. Check that out. Okay. So I'm going to try to keep this a little short, but I want to move on to our last example. That's what I wanted to tell you about principal ideals. I told you their definition, gave you a couple of examples. The integers certainly should be your guiding example of what a principal ideal domain is. But now I want to take a look at this matrix example. So I'm actually just kind of explicating an example that your author Erstein does in his book. It's example 7 that starts on page 144. So if you want to look at that, in addition to what we're doing here, we're talking about the same example. It's an example inside the 2x2 ring of matrices. So I'm looking at M2R, which you know is 2x2 matrices with real number coefficients. I'll remind you that that's a non-commutative ring with unity. Yeah, the matrix ring matrix multiplication isn't commutative, but there is a multiplicative identity, the 2x2 identity matrix. And the ring I'm actually going to consider is just a part of that. The ring R is this set of 2x2 matrices that are determined just by two numbers, A and B. Why just two numbers? Because I insist that the lower left corner be 0, the two diagonal entries be equal to each other, but the upper triangular entry can be anything. So it just takes two numbers to specify those. It's certainly a subset of all 2x2 matrices. It's a proper subset of it, the real number coefficients. And I'm going to leave this as an exercise to you, but that's a subring of the matrix ring. I haven't said this word yet, subring. You can guess what it means. It's a subset of the ring that's also a ring under the same operations. To show it, just show that it's a subgroup. I think it's pretty clear that this set R is closed under addition, additive inverse, and contains the 0 matrix. Show it's a subgroup. This is your exercise. And then show it's closed under multiplication. If you have an additive subgroup of a ring that's closed under multiplication, then it would be a subring. Cool. So that's a little exercise for you, second one of this lecture. And now I want to specify a set I. I is going to be those elements of R whose diagonal entries are both 0. Okay, so I is specified just by a single number. It's a 2x2 matrix specified by just telling me what its one possibly non-zero entry is in its upper right-hand corner. Okay, third exercise of the lecture, I'm farming out a lot to you. It's an ideal. So what does that mean? You have to show its subgroup, show that I is closed under addition, additive inverse, and contains 0. And then you have to show it's sticky. And here it's a non-commutative ring, so you really have to check those in both orders. So I'm kind of giving you a hint. Take an arbitrary ring element, something that looks like x, y, 0, x, and multiply it by an element of I, and do it in both possible orders, all right? And what are you going to show when you do this? I'm not going to do the matrix multiplication for you, but to be an I, you better get zeros in those three components. You don't really care what you get up there. So you complete the details here, but both of these things, you guys know how to do matrix multiplication. You like, for example, this one entry there, I would take the first row and the first column of those two matrices and take their dot product. And while I'm highlighting it, you can see that entry would be x times 0 plus y times 0. Okay, great, that's 0. Compute the other 4 entries. In this matrix as well, maybe you'll get something in the top right corner that's not 0, but you don't care because in both cases they're in I. So I'm going to leave that to you, because the question that I want to kind of talk about with you guys here is, what is this quotient ring? You know, if we have an ideal in a ring R, then the factor ring, the quotient ring, is some ring. And I'm wondering, do we know it? Is it new? Have we met it before? So always a good way to get started in answering that question is to ask yourself, under what condition do two elements of, in this case, R, represent the same cosets? When would a matrix XY0X represent the same coset as the matrix AB0A? Well, in some sense, the answer to that is always the same. Two elements represent the same coset when their difference belongs to the subgroup, the ideal, I should say, sorry. So the difference of those two representative matrices is just x minus a, y minus b, 0, x minus a, and that belongs to I. How do you get into I? Your diagonal entries have to be 0. So that matrix is in I if and only if x is equal to a. It's the only condition. Okay, so what does it take to be able to tell the difference between two cosets? Well, we have to just be able to tell the difference between their diagonal entries, right? Those two elements represent the same coset if these two elements, I mean, they represent the same coset if and only if x is equal to a. So if x is a, those are the same element. If x isn't a, they're not the same element. It doesn't depend on what y and b are. So I'm kind of getting a feeling for what this factor ring looks like. Its elements are sort of determined by the number you put on the diagonal. Yeah, and the number you put on the diagonal is a real number. So maybe I'm being a little bit irresponsible here, but I'm kind of ready to guess that it feels like this factor ring kind of feels like the ring of real numbers, the field, if you like, of real numbers. Yeah. Why? Because a real number is sufficient to specify an entire coset. If you told me, say, the real number 5, then I can describe an entire coset. I would take the matrix whose diagonal entries are 5 and 5, and then let the upper right-hand corner entry be any real number you like. And that's how I would get all the elements in that coset. So the coset kind of corresponds to the number that's on its diagonal entry. That's my loose interpretation of this. But now I got to make it precise. I've got to guess, right? We've made a guess for what the factor ring is isomorphic to. So what do? We're going to try to use that first homomorphism theorem. Let's try to use the first homomorphism theorem to prove our guess is correct. If everything goes through, our guess is correct. If we get stopped, we'll see how to adjust our guess. So we need to start by finding a function from our ring R into our guessed target, the ring of real numbers, which unfortunately is also pronounced R. So I need a map from R to R, but you're looking at what R's I have. And I need a map from R to R that's going to send precisely the elements in I to 0. Yeah. So the elements whose diagonal entries are 0 need to be in the kernel and nothing else. And I need to have this sort of whole coset get associated to the real number that determines it. The real number that determines it is that diagonal entry. So I would say that all of that means that we should try something like this. Let's try to see if this works. Let's send the matrix AB0A, that's an arbitrary element of R. Let's just send it to A. Yeah, at least that's a real number. And I have a feeling that this kind of feels right because, after all, we said the entire coset is kind of dictated by A. So that entire coset is going to go to the same number, and that should be kind of how a homomorphism collapses things. All right, so what do we got to do? We got to use the first homomorphism theorem. To use the first homomorphism theorem, we need, it's a 3-item checklist. these three items, we need phi to be a ring homomorphism. I'll write out some of it. We need phi to be onto. I think that that's kind of obvious, but we'll see it. And then we need to show that the kernel of phi is exactly this ideal R. So if we can do those three things, then the fundamental homomorphism theorem tells us that we are correct, that our quotient ring, our factor ring R mod I, is isomorphic to the field of real numbers. Okay, let's see. Let's get going here. Let's take a couple of arbitrary elements of this ring. I'll call them A, B, 0, A. We already used them, so let's use the same X, Y, 0, X. Yeah, and I want to show phi is additive, for example. So I want to look at phi of their sum. I don't know how to take phi of something until it's a single matrix. So let's add those matrices. You add matrices by adding their entries. 0 plus 0 is 0. So there's the sum of those two matrices. And by the definition of phi, it's A plus X. Phi of this matrix is just the diagonal entry. And certainly, that's equal to phi of the matrix A, B, 0, A, plus phi of the matrix X, Y, 0, X. Yeah, so phi is a group homomorphism. That went pretty smooth. How about multiplication? Matrix multiplication is a little trickier. I actually wish I would have left that additive part to you and just done this, but let's take A, B, 0, A, and we got to multiply it this time by X, Y, 0, X. All right. So when you multiply two matrices, like I said before, like say for this first 1, 1 entry, I want to take the row of the matrix on the left and take its dot product with the matrix on the right. So I'm going to get AX plus 0. So the 1, 1 entry of that thing is just going to be AX. How about the first row dot the second column? We're going to get AY plus BX. Down in this lower corner, we're going to get 0 plus 0. And in the 2, 2 position, we're going to get 0 plus AX. Okay, notice that that matrix is again in R. It should be. R is closed under multiplication. And what is phi of it? Phi of it is AX. And that's certainly equal to phi of our matrix A, B, 0, A, phi of X, Y, 0, X. All right, so phi is a ring homomorphism. Why is everything going so smoothly? Because we have the right phi. Usually when you're using the fundamental homomorphism theorem, the first homomorphism theorem, if things aren't going smoothly, you probably don't have the right map. Why is phi onto? Well, given a real number A, there's lots of matrices that will map to it. All you need to do is make sure you put AA on this corner. The lower left corner has to be 0. You can put anything you want in the top right corner. This is more of a proof writing comment than it is a mathematical comment. But when you're doing something like this, be specific. Don't write a B up there and then let the reader wonder what B is. Pick something. Pick a real number. Pick 1, pick 0, pick pi, pick something, but just put it in there so the reader doesn't have to wonder what it is. It doesn't matter what it is. Phi of this matrix is A. So that shows phi is onto. All right. Last thing to do is calculate the kernel. But we cooked this up to work. I mean, what does it mean? A matrix A, B, 0, A is in the kernel of phi. Well, that's true if and only if phi of it, A, B, 0, A, is the identity. But phi of that matrix is A. Yeah. So that's if and only if our matrix A, B, 0A is equal to the matrix 0B, 0, 0, which is an element of I. So I kind of did this messy, and I did the pick a point proofs all at the same time. But if you like, I'll just highlight. If you choose something in the kernel, I deduced it's in I, right? So what does that mean? That means that the kernel is a subset of I. And then conversely, if you pick an element in I, take phi of it, you'll get 0. So you're in the kernel. So those if and only ifs, the arrows that point this way, if you like, show that the kernel is a subset of I. The arrows that point this way show you that I is a subset of the kernel. All right, so by the fundamental homomorphism theorem, or the first homomorphism theorem according to, for rings, this factor group of matrices modulo the ideal of the kind of upper triangular matrices is isomorphic to the field of real numbers. We're going to see in our video lecture for Friday that means something kind of special about this ideal I. All right, we're going to leave it at that. Thanks for listening.